So hello and welcome to the database assignment 4 video. So our database uses the horizontal sharding to partition data across 3 Docker containers. So you are looking at the various two types of table. First is the replicated table. Medicine, inventory, prescription slots, and audit log are all identical across the 3 shards. This ensures that every shard has the reference of data we need. Secondly, sharded tables, member, doctor, patient, appointment are partitioned. Noticed how each shard has its own table. Shard 0, uh, uh, shard 0 member, shard 1 member, shard 2 member. You can see over here. So how does a member get assigned a shard? We use the MD5 hash function. So member ID modulo 3. For example, member 1 gets hashed, the result is divided by 3, and the remainder determines which shard 0, 1 or 2 they belong to. Here we see the member examples routing to different shards based on their hash. So as you can see, this one shard 0 members, shard how many records are there based on these shards we can see over here. So the key takeaway is members are hashed and distributed evenly across the 3 shards. So this is for the part 2, that is query routing. When a patient logs in and queries their appointments, our routing layer calculates which shared shard they belong to using some same hash function, that is MD5 of their patient ID mod 3. This determines the exact shard, in this case shard 0, 1 or 2. This query then goes directly to the shard. It doesn't broadcast to all shards. It doesn't search everywhere. It goes straight to the patient's home shard. Here is why this matters. In a traditional single database system, every query competes for logs and cache. All patients' queries hit the same database, causing contention. So with sharding, patient one's query is completely isolated on the shard. Other patients on the other shards are unaffected. Their queries run in parallel without competing for the same resources. So the result is latency drops from 50 to 100 milliseconds to 15 to 30 milliseconds because less log contention and better cache locality on the smaller dataset. So as you can see here, the patient ID, you can see the query routing to the correct shard. That patient ID 1 is on shard 1, and we can find the patient Amit Sharma on shard 1, and we can also see the appointment ID. Other shards remain unaffected. So we can say that single shard queries are fast and isolated from the other patients. Now let's look at the range query requesting all members across the entire system. Since members are distributed by hash, we don't know which shard they belong to without looking for members. So the solution is broadcast. We send the query simultaneously to all 3 shards. Each shard searches its local table and returns its member. Shard 0 has 7 members, shard 1 has 3, shard 2 has 7, something like that. So the application layer collects these results and aggregate them into the complete list. So as you can see, this is the list, like shard 0 list, then shard 1 list. This has shard 1 has 4 members, shard 2 has 1 2 3 4 5 6 7 8 9 10 11 members, shard 2 has this many members. So we combine them into the single list, and we can see that did we get all members. So you can see over here, so there are in total 23 members, and you can see that we get 23 members. So let's see. So but there is a key difference that single database, even though we query 3 shards, they run in parallel, not sequentially. So instead of taking 3x longer time, the time is roughly the same as single query because all 3 shards process simultaneously. Plus each shard is working with less data, fewer rows to scan, better cache hits, less log contention. So even with the broadcast, we are still faster than querying one giant table. This is the trade-off of sharding. Single shard queries are lightning fast. You can see that. But range queries are that touch all shards are slower than they would by keeping them on only one server. Though still competitive due to the parallel processing. So we have verified that all 23 members that are in the range query got in terminal. Let's see the cost analysis why the range queries are slower. So you can see the single shard query, example patient one's appointments, one query and one shard. So we take about 15 to 30 milliseconds. That is very fast. But the range query, we have to send 3 queries to 3 shards in parallel, 15 to 30 milliseconds each. Total time will be maximum of 15 to 30 seconds, not some because parallel execution is there. But must coordinate and aggregate results. We get plus 5 to 10 minutes overhead. So we get in total 25 to 40 milliseconds, still faster than the single DB search single DB search, which takes about 50 to 100 milliseconds due to smaller data sets per shard, better cache locality and better processing, as you can see over here. So key takeaway is that range queries broadcast but still benefit from sharding. Now let's discuss the part 4 of the video, that is the trade-offs. So sharding gives us three major improvements. That is, firstly, 3x throughput, that is 1000 to 3000 requirements per second. 2x or 3x lower latency, like 50 to 100 milliseconds to 15 to 30 milliseconds, and also 3x storage, like 1 TB to 3 TB. But we make it trade-offs. So the cap theorem says that pick two out of three, that are consistency, availability, or partition tolerance. So we picked over here consistency and partition tolerance. Firstly, let's discuss why. Because this is the healthcare system. Medical data must be accurate. If there is a network split, we guarantee correct data even if shard temporarily goes offline. We don't want conflicting patient information. That's unacceptable. What did we sacrifice? That is operational complexity is increased. We manage three different databases. Cross-shard queries are more complex. Infrastructure cost tripled. But that's the correct trade-off. For a healthcare system at a scale with 1,000 plus patients, sharding is essential. Without it, the single database collapses under load. Thank you.